The last lesson in this unit, looking at slope, is slope as a rate of change, which is probably the most mathematical way of thinking about slope. So in the math world, slope is the ratio of the vertical change, and I'm going to change the symbol to delta y, and the horizontal change, delta x, between two coordinates on an xy axis. Now this little triangle here is the Greek letter delta, and it just means change. So that is the Greek letter delta, and it just means change. So when we looked at slope as rise over run, this is exactly the same idea. Vertical distance change versus horizontal distance change, the ratio between the two. And those have real world applications, water slides, wheelchair ramps, etc. What we looked at them. But what we're looking at today is just the mathy idea of slope. What is the slope of a line on a grid? And we have a formula for that. And the slope formula is m is equal to delta y over delta x, change in vertical distance over horizontal distance. And here's how you find the change in y over the change in x. These subscripts represent the point. We always need two pieces of information to find the slope of a line. So x1 is the x coordinate of point 1, and y1 is the y coordinate of point 1. And similarly, x2 and y2 are the x and y coordinates of the second point. So in finding the slope of a line using this formula, it's very important to identify the 2 points. So in our first example to the right, here's this line, and we want to figure out the slope of the line between those 2 points. Now, it really doesn't matter what you call point number 1 and point number 2. But I'm going to call this point number 1, and I'm going to call this point number 2. So right away, I'm going to note to myself the coordinates of point number 1 and the coordinate of point number 2. And the coordinate of point number 1 is 3, 5. So this is what we did in grade 8 and grade 9 and grade 10. We found coordinates of points, and remember, you always start at the origin. You always go in the x direction first, so we go over to 3, and then we go up to 5. So there's 3, 5. And similarly, the coordinate of point number 2 is 6, 10. Now, recall then that this would be my x1, and this would be my y1, and this would be my x2, and this would be my y2 in our formula. All we're going to do now is we're going to plug the numbers into the right spot. So slope is equal to y2 minus y1. There's my y coordinate for point number 2. There's my y coordinate for point number 1. And we have 6 over 3. And when we simplify that, we get 5 over 3. So the slope of that line is 5 over 3 using the slope formula. If you have nice points and a nice picture, then you can simply do it pictorially. And honestly, I like a picture. So this idea of rise is the vertical distance between 2 points. And I'll illustrate it in green. There's the rise. There's how much higher up point number 2 is than point number 1. And if we counted that, we'd go up 5. And by convention, up is positive, down is negative. And if we wanted to determine the run, the horizontal distance between these 2 points, then there is the vertical distance between these 2 points. And I'm going to the right tree. Right is positive, left is negative. And instead of using a formula, I can simply count. How far up do I go? How far across do I go? And I express that as a ratio of rise over run. Well, here's another example. And again, same idea. We identify our coordinates. Here's coordinate 1, here's our coordinate 2. So coordinate 1 is at 1, comma 7. So again, we go from 0, 0. We always go the x direction first, and then we go our y direction. So we go right 1 up 7. There's 1, comma 7. And coordinate 2 is 7, comma 4. And if we wanted to use our slope formula, the slope of that line is equal to y2 minus y1, so 4 minus 7 over x2 minus x1, 7 minus 1, we get negative 3 on top, we get 6 on the bottom, and if we wanted to simplify that, we get negative 1 over 2. So one of the things in the mathy world that we haven't really encountered so far is this idea of slope can be negative. And it really just represents which way the line is going, and we're not really going to have to worry about that too much. So this negative just represents which way the line is going. If we wanted to do this pictorially, again, we could simply go, okay, if I start at 1, what is the vertical distance? What is the vertical distance between these 2 points? Well, I have gone down 3. And again, up is positive, down is negative. And then I have went right 6. Right is positive, left is negative, and there's our negative 3 over 6. So in the mathy world, we have a formula where we can just count the rise over run. But there's no story here in these examples. But there can be a story. And probably when I said slope is a rate of change, the rate of change that everyone knows is velocity. We've all driven in cars. You might be driving a car, and we have to be really aware of how quickly we're going. So the rate of change is a comparison of two things with different units. So distance versus time, kilometers versus hours or seconds or whatever you want to do. So here's two pictures of a car, one car going 50 kilometers an hour and one car going 75 kilometers an hour. And if we plotted the information, that's what it would look like. These two graphs would look like this. Now, obviously, the car who's going quicker, 75 kilometers an hour, will go a further distance in the same time. And that's kind of this illustration right here. In 1 hour, there's a difference of that. In 2 hours, there's a difference of that. In 3 hours, etc. So the 75 kilometer hour car, for every hour you travel, it's going 25 kilometers more. But I just want to illustrate with one quick example this notion of slope as a rate of change. We want to figure out what is the slope of these two lines, and we'll see what that spits out, and hopefully that will help us with our understanding. So we can determine the slope of these lines by choosing any 2 points. So all I'm going to choose in the dashed line example, I'm going to pick these 2 points, 1 comma 75 and 2 comma 150. So I'm choosing these 2 data points right here. And I could count if I wanted to. I could go up and I could go across. I have to be careful with scale, but that would be okay. But I'm going to use our slope formula. So using our slope formula, here is y2, y1. So here's our 150 minus 75. And here's our x2, and here's our x1, 2 minus 1. And when I do that calculation, I get 75 over 1. And remember the units of the top. The units of the top, the vertical, the dependent axis is distance in kilometers, and the horizontal is time in hours. So in looking at this, we found the slope of that line, and the slope of that line actually represents something. It's not a measure of steepness. When you talk about driving in a car, you don't talk about steepness, you talk about how quickly you're going. So Here's what we mean by slope as a rate of change. By figuring out the slope of this line, this story, it really tells us how quickly the car is going, rate of change. And if we do the same thing with with the solid line, again, I'm just going to pick 1 comma 50 and 3 comma 150, and those are 2 points on the line. If we figure out the slope of this, we're going to have our y2, y1. We're going to have 150 minus 50, and we're going to have our x2, x1, x2, and there's our x1. And what we end up with is 100 over 2, which is 50 over 1. And remember, our units are kilometers on top and hours on the bottom. And the slope of the line represents something physical and understandable, represents how quickly the distance is changing compared to time, which is called velocity.